This is about why language models hallucinate, and it's joint work with three researchers at OpenAI. Adam Kalai, who's been my primary collaborator on this work and who led the effort, Ofir Nachum and Eddie Zhang. And yeah, so what you see next are this is Adam, and this you may or may not realize is also Adam and not a hallucination. So you've seen these things by now many times, and especially in your community, all kinds of hallucinations or false statements and the problems they cause. This morning I asked when was David Birch born? Respond if you know with DDMM. And it says David Birch, the American navigation expert, was born on March 3rd. He's not here, but I doubt that's correct. The reason is because I asked again, and then the date of birth changed. Um, Here's a different example. How many R's in strawberrier? Which is, by this point, how many R's in strawberry probably has thousands of uh, occurrences. And this one tells me it's three, along with a breakdown. Um, of course, it's actually four, right? And then it also offers help with spelling and if I need help with a different word. I tried again, and again I get three. And then I said, "How do you know?" So it tells me it's a good question, and then also tells me how to count, but skips the last one. Yeah, so um, this is a continuing problem as of this morning. It is in the Merriam-Webster's dictionary as a or false, plausible but false or misleading response generated by an AI. Since 2023, this definition has been there. Yeah. So this is a bit vague for us, right? Even though we can recognize it. So in this talk, the definition will be much more concrete. There's going to be a set X, capital X, of possible generations, if you like, which could be completions or documents, whatever. And within that, there's a subset that we'll just call valid, whatever that means. There's a valid subset. And then there's a subset that are plausible but invalid, and those are going to be hallucinations. The reason I say plausible is just to avoid, strings that make absolutely no sense and wouldn't even show up in normal documents. So it's just a subset of things that you're calling valid. So maybe in a world where you need facts based on experience, there would be facts. In a different world, it could be grammatically correct sentences and so on. So there's valid, there's hallucinations, and those are the two subsets of all possible strings that we're interested in. So here's the outline of the talk. What are hallucinations? And we've kind of seen this. And then focus on the two aspects of building these models, pre-training, where the main sort of message will be why avoiding hallucinations is actually harder than classifying them. And in fact, we'll directly relate hallucinations to misclassification, which is the problem of determining whether a given statement or is actually valid or not. That's all, just saying yes or no. Uh, and then how to estimate the hallucination rate. Then we'll briefly discuss post-training, which is in part designed to reduce hallucinations. And one of the main issues is how current evaluations penalize errors and uncertainty expressions like I don't know in the same way. So the oversimplified takeaway number one is that pre-training encourages hallucinations, and this will be provable, state a theorem to this effect. And the oversimplified takeaway two is that post-training should penalize errors more severely compared to I don't know, other forms of uncertainty. And this is a recommendation. Okay, so just so you know what I view these things as, and not because, I mean, this very basic, I would assume for this audience. Suppose your corpus consists of just these 10 documents, if you like, sentences, each of them occurring with probability 10%, right? So equally likely. Um, then the way you would, a language model would generate documents would be that, you generate the first word with probability 40%, the probability that it is the first word in the training data. And then given the first word, the probability of the second word is sun with 50%. in the training data, and that's what an ideal trained LLM should do. And then, given that the first two words are the and sun, the third word is rises with probability 50%. And so the probability of the sentence the sun rises is the product of these three, which is zero point 0.1, and that's correct. Now, so the point, and kind of a crucial, simple observation is that if you want to build a model that maximizes the likelihood of generating the data that you actually saw, that you trained on, the expected log likelihood, then what you could do alternatively is simply maximize the next token probabilities, and that's a much more concrete thing to do. So that's the goal of pre-training. You have some language distribution P, and for the purpose of this talk, we'll assume that the training data, the training distribution is only over valid things. So of course you could be hallucinating because you were taught invalid things and wrong things and so on. But let's just say that the training data is actually being verified to be valid. That's the training distribution P. And then your goal is to learn a language model P hat using uh, data drawn from the valid distribution, the distribution supported on only valid documents. Okay, so then the goal is to find a P hat or parameters of P hat, whatever be the architecture. We won't even get into that at all, so that you minimize loss. Same thing as maximizing likelihood, minimize the log loss. To this, you could add prompts and so on. Here I'm talking about entire documents, but you could say, complete this prompt to maximize likelihood. Now, in principle, of course, language models don't need to hallucinate. You could always just say a valid thing, or you could memorize everything that you were trained on and only output over a distribution on these valid things. The problem, of course, so this suggests there's no hallucination here. The trouble is that these are not calibrated. They're not doing anything beyond the training data. There's no generalization. And I'll get into what that means. But here is an example, maybe that'll make things even more clearer. So suppose this is your training data. You have 10 sentences. But you might notice that 5 of them are the same thing repeated. It's Alan Turing's The Day He Died. And the other 5 are random people and random days. But in fact, these are valid. Okay, so there are 5 valid things. Now, if you were to train on this, the model that fits this would be, well, half the time you output Alan Turing's date, and the other half, it's a random name and a random date. And of course, in the training data, you only output the true ones, but that's what it looks like. Now, this language model, if you were to use it, even though it fits this so well, would generate 50% hallucinations because random name, random date, you only have a 1 in 365 chance of getting it right. This language model is calibrated, but it's bad for generation or even predictive typing. The other alternative would be to simply memorize this training data, what you might call a stochastic parrot. So it memorizes this with the correct distribution. So for half the time, you still say Alan Turing died on a certain date. And the other half, you just split among the training data documents according to how they occurred. And so you're always outputting something that's valid, but the trouble is that it's not calibrated because these other 50% are overrepresented. They should have been almost zero probability, and they're getting 10%. So, you're not doing anything interesting here. Okay, so the main intuition here is that pre-training is designed to match the data distribution over the training data documents. And in particular, this means it will calibrate with the training distribution. And you're going to see future documents from the data distribution. They'll have some fraction of unseen. If you've seen everything that could possibly be true in the training data, then of course we won't hallucinate. But assuming you haven't seen everything that's possibly true, then there will be a chance of seeing of unseen things, and then there you will hallucinate. That's the rough intuition, but let's formalize this because it's kind of vague. Um, so calibration, I've already mentioned what it is, but it's just the idea that rather than being accurate, where you're precise about every probability, you just want to say that on days when you say, it's going to rain 20% probability, on all those days, if you put them together, it actually rains 20% of the time. So that's the same thing, but skipping ahead, just the only point of the slide is that calibration is a much easier goal than being accurate. So for example, you could simply output for every document the average probability in the training distribution, the same answer, but average. So you just say through the whole year, the chance of rain is 5% if that happens to be the yearly average. And then that's calibrated because on days when you say 5%, which is every day, the average is 5%. So it's a much weaker goal. And indeed, after pre-training, um, the language models are very well calibrated. This is the input output matching the probabilities. On the other hand, after post training, you lose this calibration, but of course you also reduce hallucination, which is one of the goals of post training in all the ways that it's done. So here is the main message that I want to get across about why why this what's happening with these hallucinations. So suppose this is your training data. For now, it's a simple case when you're getting full sentences, 3 valid statements. And let's consider a different problem. So the normal problem is generation, right? Or completion. You're given part of a document and you're asked to generate things. But classification problem, the corresponding classification problem is you're given a sentence and you just want to know, you just want to output plus or minus. Is it valid or invalid? That's the problem. Is it valid or not? So this is like a traditional supervised learning problem. You're given data. So in this case, the green statements are true and the red are false, and that's your training data. And now given a new statement, you'd like to be able to classify it. So it's unsupervised learning versus supervised learning. The point is that supervised learning is much better understood, much more studied classically and so on. And our main theorem, which is here stated informally, and in the next slide I'll state very precisely, is that the rate of hallucination, so generating invalid statements, is at least twice the rate of misclassification minus a correction term. So in other words, if you can't distinguish fact from fiction, if you can't distinguish true invalid statements from valid statements, then you will hallucinate. Okay, so this can't quite be true as I stated, right? Because you could always just output one statement like we said before, or just say, I don't know. Just say, I don't know all the time. Well, the point is that that's what the correction term is for. And let me now state a more precise statement, inequality. So the left-hand side here is the probability that your learned language model outputs an invalid statement, outputs an X, which is not in the valid set, right? And that's at least twice the probability of misclassification on what distribution? Here's the distribution. It's the most natural one you can think of. With half probability, you see a valid statement from the same training distribution as your language model was trained on. And with half probability, you see a uniform random invalid statement, uniform random hallucination. So half the time, it's a random hallucination. Half the time, it's a valid statement from the same distribution that you're trained on. And your goal is to correctly classify plus or minus. So the probability that you get this wrong, that's what's being captured here. So this hallucination is at least twice this minus these 2 correction terms. The first correction term is, I'm just expanding. So actually, before I get to the correction terms, you might say classification by what? You could say here the best possible classifier, but that's sort of a complicated statement. In fact, we'll pin it down to a very natural classifier, which is the classifier based on the language model that you learned. So if you learned a language model, what it does in the most basic thing it does is given a sentence or a generation, it tells you what is the probability of that generation. And so the classifier is just if that generation probability is higher than a certain threshold, we'll say it's plus. If it's lower than a certain threshold, we'll say it's minus, meaning it's a hallucination. So that's the classifier, the threshold classifier. Okay, and I'm choosing the threshold to be just 1 over the number of hallucinations. So now the statement is very precise. For any learned language model, the probability of a hallucination is at least twice the probability of misclassification by this threshold classifier minus this correction term is just the fraction of the universe that's valid. So if the entire thing is valid, then you don't have any errors. And this last part is the calibration error, which is just how far off are you in the total probability you assign to statements with probability more than, in your world, probability more than 1 over this h. So you don't need calibration on every probability, just on this entire set. So that's the full statement. And I see that I'm getting close to the 20-minute timeline. So I'm going to just say one more thing precisely and then go from there. And this, you don't need to read the first half of the slide, but basically minimizing loss, log loss, and even going to a local minimum, you don't have to globally minimize, implies the calibration that we are talking about. In particular, this error term that we saw on the previous slide goes to zero at any local minimum of the log loss. You don't even have to globally minimize it. So that's the statement here. And we can extend this to prompts and responses to prompts and to other. And so what does this tell us? You're able to pin down causes of hallucination to corresponding causes of misclassification, which we understand much better. So, for example, one common cause of misclassification is the model that hasn't seen enough data. The sample complexity of the problem is very high, like in the case of birthdays, for example, and and that's why you misclassify. Another cause could be a poor model, and then one could be another cause could be it's computationally you need a huge computational effort to do it, and that's why you're misclassifying. So whatever it be, you can relate them correspondingly. Now this was going to be a proof, which I will skip. It's just a 2-slide proof of this reduction. There are also statements which are much more concrete, which meaning what I showed so far is a reduction. You can remove the reduction out of the picture and say that for certain families of statements, such as arbitrary facts like birthdays or who ate what, when, where, you can actually relate the hallucination directly to something called the missing mass. What fraction of data haven't you seen? Which turns out can be estimated just from the training data. In particular, if you haven't seen this, there's this very nice fact from all the way back to Turing, which says that the fraction of missing mass is the fraction of data in your sample that has occurred exactly once. And this gives us a standalone theorem with not a reduction about the hallucination rate. All right, so I think I should say one more thing about post-training and stop. So post-training today, it's this art with lots of very sophisticated techniques and human effort. Um, but and it is designed to abstain, of course, partly. One issue that we found is that, I mean, that's well known, is that the score of getting a wrong answer and the score of abstaining is the same, just like in the SAT today. So if that's the case and you're minimizing log loss, why would you ever abstain? Because abstain gives you the bad score for sure. Guessing gives you, a small chance of the right answer. And nevertheless, if you look at the evaluations, the benchmarks today, basically they all have this binary grading, correct or wrong, and wrong and I don't know get the same penalty. What we'd like to do is answer, the language model should answer only if sufficiently confident. Whatever sufficiently means could depend on the user, could depend on the context, and so on. So, for example, you might add to the prompt, respond only if you're at least T confident, T being between 0 and 1. And actually, you could also change evaluations only in the scoring to achieve this. A correct answer gets 1, I don't know gets 0, and a wrong answer gets a negative number T over 1 minus T. The choice of this is designed so that it doesn't make sense to guess unless you're at least T confident. The expectation would be below 0. So that's why that's the right choice here. And we're calling this behavioral calibration. So you output an I don't know if the model's confidence is less than the target confidence for that particular question. So here is my last slide. Pre-training produces these predictive language models, and it's great. It optimizes the predicting text from the training data, and it gets some things correct, which I don't understand why. It's still a mystery to me why grammar, for example, long range structure is correct. It's wrong on people's birthdays because no matter how much data you have, as long as you haven't seen somebody's birthday, your chance is 1 in 365. It's correct on country birthdays because you've basically seen them multiple times, and there's no reason for you to be wrong. It shouldn't be wrong on. There's no reason it should be wrong on citations, even though it used to be. And post training produces language models that shouldn't hallucinate in principle, and we'd like to encourage abstaining, which currently most evaluations, in fact, encourage random guessing. So I am happy to stop here. Take a few questions.
Great. Thank you so much. Thanks so much for the presentation, and thanks for making it so digestible. For any of you that have not taken a look at the page from OpenAI, it's also a really, really great read and a very quick read. So I highly recommend it. A lot of it parallels some of the ideas that Santosh talked about right now, and I think it's a great read as well. Um, But yeah, there's a couple questions. So are are you able to see the chat, or I can just read it out to you?
I mean, if it helps the audience, you're welcome to read the chat, but whatever you
Here,
prefer. Yeah.
I can just read it out to you. So first question says, in the paper you've mentioned n-grams to illustrate the architectural limitations of models that compound to the statistical lower bound error rate. It's obvious how from such limited context windows, it's sometimes impossible to correctly predict the next word, which leads to hallucinations. But did you study or have examples on the models such as transformers with larger context windows?
Right. So the point of the paper is that the statements we've made are based on statistical considerations independent of the model. So an example like birthdays, it doesn't matter how complex or how large your model is, you're simply not going to be able to do it. What we call arbitrary facts. And more generally, whenever the corresponding classification problem is hard for whatever reason, whether it's the model insufficiency or statistical lower bounds, the hallucination rate is going to be there.
Okay, thanks. Next question. You mentioned in the paper that delta, the calibration difference between p hat and p, is small near cross entropy optima. But usually the model isn't perfectly optimized. Did you measure this delta across domains, and does it affect the bound usefulness, or is it always assumed to be small compared to the classifier error?
Oh, right. So first point is that we don't need to globally optimize the log loss to achieve calibration. Just a local minimum is fine, and almost any gradient descent style method converges rapidly to some local minimum. Even you don't have to assume anything about the structure of the local minima and so on. That's one. Second, while although I haven't done it, there is parallel work that we cite by Kearns and Meow that actually measured calibration errors and hallucination rates and found that they actually correlate pretty well in various in some domains. I won't be able to tell you right now which ones they did it on, but it's out there, their paper.
Great. Okay. Next question is also the reduction on screen I assume that this is talking or like mentioned referencing a specific slide. The reduction on screen assumes uniform sampling over our set of errors E, whereas error distributions are realistically not that simple. Did you study how sensitive the bounds are to replacing the uniform threshold 1 over E with a more realistic non-uniform distribution?
Yes, absolutely. Yeah. So we're trying to present the in some sense what should be the hardest situation or the most natural situation. But as long as you have training data where half of it is error and half of it is fact drawn from your training distribution, even if all we need is that the errors have the error distribution, the hallucinate in the data has some entropy. If the error is concentrated on only one item with half probability, you always say one wrong thing, then the model will learn that wrong thing and never get it wrong. But as long as there's entropy in the error part of the training data, then the model will hallucinate. The reduction works still.
Gotcha. Okay. And before you get to the next question, a couple of the audience members are requesting that if possible, the slide deck could be shared. So is that something that we can get out? I'll reach out to you later if that's
Yeah,
something that
sure. I'm happy to send it to you. Yeah.
sounds good. Okay. All right. Next question. In practice, when we audit AI systems for governance or compliance, we usually don't have access to retrain the model. Is there any practical way to tell if a model is incentivized to guess? For example, a proxy metric or behavioral signal we could measure just from its outputs.
That's a good question. And indeed, we're thinking about how just from the output behavior, one could one could map, the model's confidence level to the target or true confidence levels, if you like. And so, at the least, one hopes it's monotonic. Like if you say answer only if you're, 50% confidence versus 90% confident versus 95% confident, you can track what is the fraction of the time it's saying I don't know, and hopefully that at least that's increasing. So if that's a monotonic function, it'll be nice to be able to have that down for a model at a time so that you know what you should say. So you want it to answer if the true confidence is 90%. And so maybe you have to actually say 95, right? And so this mapping is something we're trying to figure out, but hopefully there's a way to do it just based on output behavior. But it's a good question.
Gotcha. Okay. And then another question is, other than lack of training data related to the question, can you talk about other reasons for hallucination? For example, in creative tasks where training data is not supposed to exist at all.
I'm sorry, I didn't quite understand the question.
So I think the question is just asking about like maybe I know you mentioned like you talked about this a little bit earlier. If you wanted to maybe clarify again the additional reasons for hallucination other than like lack of training data. Like for example, in and the question mentions,
Right.
for example, in creative tasks where training data is not supposed to exist at all.
Good. Yes. So I'm I wouldn't. So in creative tasks, also, it's a question of what you would call hallucination or not. That's a little bit more difficult. But let's say in other systematic tasks, such as addition, which now the language model gets right, but they used to get wrong, or this counting tasks, which in principle there's a very simple rule that'll make sure you count correctly, and it's still getting it wrong, as you saw in my early examples at the beginning of the talk. So it needs very little data in principle. So the question there is the point there is that the model is somehow not yet sophisticated enough to answer. It's not a matter of training data. Um, there are other instances where it's computational difficulty. It's not about sample complexity. It's actually computational difficulty. For example, if I have a sentence of the form, the prime the factors of and a big number, thousand digit number are so and so and so. Okay. Now, this entire sentence, if you stopped at the point, the prime factors of this x are, would be very hard to complete because as far as we know, factoring integers is a very hard problem, and the basis of cryptography still. But if you were to just ask to say, generate the entire sentence, what you could do, generate sentences like this, what you could do is pick primes randomly, multiply them, and then form the whole sentence. Now, that wouldn't be a regressive, not autoregressive generation, but it illustrates the difficulty of generation versus you know, um, um, completion.
Sounds good. Okay. We have, I think, a couple more questions and then we're going to cap it off at that, if that's okay. So one more question is, you also mentioned that this lower statistical bound is unavoidable, as demonstrated through your reduction classifier, and even when the training data has no factual errors. Do you have a training data set in mind that has no factual errors, which we can use to test these bounds ourselves?
I mean, I tend to be a believe people. Things like the dictionary and Wikipedia and other sources are trustworthy. Historical facts, about dates and so on, which you can get from the encyclopedias. So these I presume are I would assume are factual. Yeah.
Okay. All
Yeah.
right. And then last question. Explicit confidence targets in evaluation can be gamed. The model could output, I don't know, at every question. Have you considered penalties for excessive abstain responses too?
Yeah, so that's I mean this is part of the reason why I think these companies are not do not have incentive to say I don't know, because uh, users will be put off if it's answering I don't know all the time, especially for questions that they know the answer to, but they want to see what the model says. So I think there's a natural incentive not to say I don't know. I would be worried about not saying I don't know enough or not expressing uncertainty enough. I mean, that's kind of the problem. I think the issue of excessive humility or excessive, being too careful is not a problem today, the way it's set up. Yeah.
Okay, great. Well, thanks for answering these questions and thanks again for the awesome presentation. And we'll get the resources out to you guys, such as the recording. And yeah, again, please check out the paper if you have a chance. Some really great concepts in there that Santosh has just covered. But yeah, uh, thank you so much for coming, everyone, and we'll catch you on the next talk. And thanks again, Santosh.
Thanks. Yeah. Thanks,
All
guys.
right. Bye, guys.
Bye.